Kia ora, tēnā koutou everyone. Thank you very much for joining us today on our webinar around H1 and insulation requirements. My name's Shane Clark, I'm the General Manager here at Nuralite. Special welcome to the NZIA Emerge group, which is a group of recent graduates who have specifically requested this topic. We thought, obviously being quite popular, we would put the invitation out far and wide. So we've got some pretty good numbers today. So yeah, again, much appreciate your time. This is 23 in our series of webinars. So all the others are available on our website. If you find this one of interest and you think the others may work for you, then by all means feel free to file through our website and find the previous ones. So yeah, as this is a bit of an intro, I just want to touch on a couple of basics. First of all, that you know, Nuralite's been synonymous with flat roofing for about 55 years, and we're quite committed to building best practice. It's one of our core values around integrity. So this is why I'm going to talk to you today about our thoughts on insulation, how it interacts with the new requirements under the H1 clauses, which we'll touch on later, and hopefully today, with our sister company Outright, combined with Nuralite, we want to touch on 4 questions and hopefully provide you the answers. We're going to first of all discuss what H1 is. We're going to talk about what the changes are and what the new requirements are, particularly around insulation. We're going to talk about some of the unintended consequences of putting too much insulation in your building. You can have too much of a good thing, I'm told. And if so, what is the best practice around roofing insulation? And hopefully there's one key message we can take away from this today, that the warm roof, we believe, is the superior method to achieving the new insulation values around H1. Now, due to the advancements in technology, if you like, we're able to beam across the country to you today via the internet. So it actually saved us money on the afternoon catering budget. So that's much appreciated. What we will do, however, is for every participant, we'll donate $10 to our chosen charity. Now, last time we did this webinar, we donated to Tier Fund, which is the Ukrainian Emergency Fund. That was very, very popular. Appreciate your feedback on that. So we're going to stick with that one for this webinar. The charity is nominated by our guest speaker. So thanks for the nomination there, John. Hopefully we're going to help the world out, and appreciate everyone attending today. We've made the world a better place. All right. Excuse me. Just a little bit about our webinar today. As I said, we've got a large group of the NZIA Emerge people here. So this webinar is actually eligible for 10 NZIA points. So at the end of the webinar, there's a survey that pops up. So put in your code there and we'll be able to populate those points for you. It's also available on the website if you can't watch this live, it's available, what do you call it, post-mortem. All right. So you'll see that I'm not the only one sitting here today talking to you, which is probably a good thing. I'd like to welcome my panelists. We've got Mr. Scott Squire, the Specifications Manager for Nuralite. And we have John Davies, the Research Development Manager from Oculus Engineering. So we're going to involve those people rather than looking at me talk all day. And just before we start, we're going to make this as interactive as possible. We're going to put up a couple of polls along the way. We're going to open up the Q&A function at the bottom of the screen there to ask away a few questions. And hopefully at the end, we've got some time to answer some of your questions. We've set for an hour. We don't want to go any longer. We appreciate your time's important to you, so we'll cap it at that. Any questions that come in that we can't answer, we'll actually populate them into a document that then get resent to all the attendees that are registered today. So if we don't quite get to your question, we will do in writing. So hopefully that helps. So right, let's kick off. Let's warm up those fingers. Our first poll for our webinar. We'll leave you a minute or so to do this. Just keen to know, obviously we've got a lot of designers in the audience, so we'd love to know if you've started to design to the new H1 standards, particularly around insulation. So I'll leave you a minute or so to answer that for us. It'd be quite interesting to see. And of course, we'll share these results with everybody who will as well. And there we go. Yeah, good. It'd be interesting. I mean, we compare that to our last webinar. We ran a similar poll. It looks like a lot more people are starting towards to lean towards designing it now. So that's good to see, in our opinion. All right. Right, we're just going to flick to the presentation mode. So we're going to sort of disappear to the side a little bit. It's probably not a bad thing. And talk to this topic. So we're just going to touch on the first question. John, what is H1?
Oh gosh, let's get right into it. Righto. So H1, what it's really commonly referred to as H1 insulation, and it's actually not. It's a bit broader than that. We've got a bit more information behind H1. So the way the actual clause is written, it's H1 energy efficiency. So that energy efficiency requirement is across energy, the use of the energy which is coming into a building. It talks about insulation, yes. It talks about the energy or the physical conditions for energy performance, and I'm reading this direct. So it provides for the efficient use of energy and sets physical conditions for energy performance. That's it. Inside that, and when you hear it as H1 insulation, it's kind of like saying a car is a steering wheel. Well, no, the steering wheel is just part of lots of moving parts, lots of elements of that car that need to come together. So in the same way, insulation is just one small part, which is why this slide has the I, the A, the V, and the H, and that's at the bottom of the slide there. Insulation, air tightness, ventilation, heating. It's a combination effort. It can't be done. We can't do a whole bulk up of insulation without considering other things, because that favorite phrase of yours, the unintended consequences, that's where that comes in pretty quickly if all you do is insulate a building. And if you insulate it heavily, you'll be growing mold pretty quickly if you don't do some other things around that.
Yeah, right. Okay, good. So H1's not a US military vehicle, per se. It's what we're talking about here today.
The Hummer.
No. No? Okay, fair enough. All right. If we just flip to the next slide there, Jade. So the other thing I understand about H1, there's a couple of methods as well, which we probably should sort of illustrate.
Yeah, do you want me to just touch on this? Is that the
sure.
Your lead in there? So what we look at is the way in which a building is going to comply with the insulation standards. And so we are talking about insulation within this. So you've got three methods there, and there's 2 points to each in the slide. So really you're either looking at individual elements, and that's the schedule method. So do you have R6.6 in the new roofing requirements? And that's not just R6.6 of insulation, that's the constructed R value. So you need to account for other elements within the structure. So, within a roof, you've got to account for the losses that you'll have going through rafters. You've got to account for losses through fixings, all that sort of thing. And we'll get to a little bit of detail in that later on in the presentation. So you need more than R6.6 in a typical roof. That's to comply with the schedule method. With the calculation method, it's a similar approach. You calculate what you've actually got across a building, and there's a little bit of an ability to trade off between areas. You can't just put none in some areas and lots in others, but that's sort of what that would suggest. And then the last one there is the modeling method, where you actually calculate, I'm using the wrong wording if you like, but you're actually modeling a real building, a real assembly, a real build-up of that combination of materials. What's really interesting with this, it's the only method that will give you an actual energy requirement output. Now that's really beneficial, because in most cases that we would find that we'd work on, we can reduce the amount of insulation in the roof. Now I'm saying that, I say reduce, but what I mean is less than a constructed value of R6.6. So you can see some of the value proposition there. You've got the ability to spend a little bit more in the modeling to save on structure, to save on thickness of roof buildup, to save on that insulation, just pure thickness. You're actually looking at how it will perform with the rest of the building, and you'll find out, and that last element there, known energy required, you'll find that out, and the modeling that we would do with the passive house planning package, for example, on any building, will actually tell you how much that building will require to heat, but how much it will overheat in summer conditions as well. So schedule, yeah, okay. Calculation method, yes, better. Modeling method, absolutely. That's for us, it's a no-brainer.
And John, on that note, with the modeling method, obviously that's being carried out before the building is being built. So, you know, there's advantages in the sense that the design can be tweaked and differences can be made to, you know, balance the approach, right?
Absolutely. You can do that. We would typically do that right at the very beginnings. You know, if we get a resource consent documentation and we've got the shape of the building, we can start modeling at that point to give some indication of how and what we would need to make that building the true warm, dry, comfortable and not overheating.
Yeah, right. Sounds like that modelling method might sort of mitigate necessity to put 800 mils thick of lofted insulation and give you an alternative to that, will it?
Yeah, well, it will tell you whether it's needed. And in some cases, you might need that, but you might be in Antarctica.
True. True. All right. Okay. So on to the next part, we're going to talk about basically what the changes are really. And I think, Scott, you're going to talk to this point and tell us where you've been on holiday, I think.
Yeah, that's right. Yeah. Thanks, Shane. So previously there were 3 climate zones. Now there's 6 climate zones. So these new climate zones, they're based on thermal modeling of buildings using NIWA climate data files from 18 different climate stations throughout the country. So essentially what that means is that we now have climate zones that make sense from a climate view in terms of energy savings, whereas previously it was largely by population, the old three zones there. So the other thing that we take account for when you look at the map here is the local government boundaries are nice and clear there. So from a designer's perspective, it's quite easy to identify which area each climate zone falls into. So yeah, it's definitely a step in the right direction. And I think one example under the previous 3 climate zones that sort of highlights that approach or the shortcomings of that approach is that Queenstown and Nelson were lumped into climate zone 3, which we all know quite different environments, you know, that varies throughout the year. So, you know, these climate zones, it's definitely a step in the right direction.
Yeah, nice.
So I've got a question there. Why on earth? Well, this is it. Why on earth, right across those climate zones, do we have R6.6?
Yeah, good question.
Thank goodness for the modelling method.
True. Yeah,
perhaps.
Yeah. That wasn't a pitch for that. No, it's a real question.
So yeah, H1, AS1. Bear in mind we're looking at the schedule method here. Whilst we've introduced 6 new climate zones, we now have a blanket R6.6 across the board. And bear in mind that's a constructed R value for the roof assembly. So we're really seeing in a lot of parts a doubling on the old requirements there. So yeah, the target is to reduce the energy and the energy required to heat and cool these buildings by approximately 40% is the target.
Okay. And just a quick question to anyone on the panel who wants to grab this. I mean, our old R values, how do you think they compared to similar climates worldwide? I'm pretty sure this is common knowledge, but let's make it common. How do you think these compared to other regions in the world?
Pretty poorly, you'd suggest.
That's very polite, Scott. Well done. Nice.
Yeah, no problem.
Yeah, certainly lower than, but you know, again, we're talking about quite poor performance of our buildings in general anyway. So you know, you're not just talking about roofs, you're talking about poor performance windows, window framing, you know, poor performance walls, poor performance floors, or low. Maybe I should just say low. Like that's our expectations of warmth in our buildings is pretty low, and that's what this is starting to, to answer. So this is an improvement. There's no way, don't hear,
Exactly.
certainly don't hear me say, gosh, we shouldn't be 6.6, and no, we should be improving, but we've got to do that in a smart way, not in a numbers way.
Agree. And I believe commercial's done something slightly different.
Yes, absolutely. Yes, we're seeing even larger increases there, H1 AS2. So yeah, the R values, and again, these are constructed R values. We've got a range of values there from R3.5 up north down to R7 down in Southland there, that's quite significant on the old requirement of R1.9. And the target there is to reduce the energy required to heat and cool these buildings by approximately 23%.
Yeah. And just keeping in mind here that we're talking about R values for roofs. I do appreciate that buildings do consist of more than roofs. We're just trying to focus on one little nugget, otherwise we'll be here for days. So yeah, we're just touching on that. And I believe there is moving and shaking going on with other building elements too, John. You guys are doing some work on the other parts that hold the roof up, is that right?
Yeah, that's so, and that'll come up in our slides to come.
Okay.
But we're talking, we're talking about the enclosure of a building. So this slide shows us the whole enclosure. So let's start with some basics. You have a continuous structure to keep the roof standing up, to keep it all connected. That's structural.
Sure.
Then what you want to see is a continuous thermal line, and that's in yellow here, and should actually include the glass. So that's just an indicative drawing, really. But that continuous insulation is super important right around the building. Then in this case, we've got a red line showing the air tightness layer. So we're wanting to keep, and that if you want to dig in and have a look at H1 really, really early on in the description of that, it talks about limiting uncontrollable airflow, or sorry, yes, limiting uncontrollable. So yeah, so limit what's going in and out of the building, because that's energy loss or gain and through your building envelope. So the envelope there is the red, the yellow line, the gray. It's right around the building. It's not just the roof. It's not just the walls. It's the floor as well. Whether that's ground connected or above the ground as a timber or steel frame suspended floor. So within that, because we're hitting higher levels of air tightness, that's why mechanical ventilation is written in there. Remember those things we had already on the second slide? The insulation, we want that continuous and at a decent thickness. We want air tightness because that helps the insulation to perform, helps stop energy loss through air movement. Then we've got ventilation, and we would argue that windows, while they can work, don't typically get opened at the right times, don't typically get opened when the wind is blowing in the right direction or if it's blowing at all. And so we would advocate for mechanical ventilation, which is running all of the time, not just an extract above your kitchen hob, not just an extract in your bathroom, but actually a whole house. That's becoming more and more common. And I think the other one there is, which is not shown, is heating. So our houses don't heat themselves. And you can argue all you like about, I'm going to orientate the building to the sun. Actually, that's unreliable. And we would be looking at those very carefully and saying, hang on, your insulation is now working well. You actually need to provide shading to prevent overheating more than you do, wanting that sun in, because you'll just cook. I think I just repeated myself on that. So the heating is actually an input into the building, and I'm going to cover that very briefly or mention that a couple of times through some slides later on.
Yeah, cool. So I think we're up to your slides now, John. Particular favourite of mine. Okay. I love these rudimentary drawings. It takes me back to my tradie days, drawing instructions on the back of cigarette packets. Quite clear to me. I'm not sure
whether that's a compliment or not.
It's self-fulfilling. I quite enjoy them. So.
Okay.
Yeah.
So look,
we'll throw it to you,
drawn these. Yep, good. I've drawn these just to pull it right back to really getting a good handle on the principles at work here. So what we're going to hit is a very basic roof structure. All of these drawings are going to be the same. I've got 14 slides that look very similar to this. I'm going to explain them. We're going to go a little slowly on the first one just so that we're all talking the same language, and then we're going to speed up as we go through. So what have we got? We've got a rafter. We've got cross-section. There's no cladding. There's no roof cavity. There's no roofing underlay here. Inside the structure, there's no internal batten. There's no plasterboard layer. There's nothing else. So we're just talking about the rafter. We've got insulation through that rafter. It's full depth insulation. So it should be, my scribble is not perfect, but it should be at the top of the rafter, at the bottom of the rafter. It should be filling that up. Now, what I've drawn in here is a Ukrainian flag, and I just want to point out that the Ukrainian flag is actually quite useful for us. It's actually got a hot and a cold side. Didn't know whether you're aware of that. Well, it does for my diagrams anyway. And what that indicates is this idea that we've got heat inside the building. So that's the warm side, the yellow side. And I've done that deliberately because our climate, when I say ours, everywhere in New Zealand is classed as a heating climate. That means that we are heating more than we are cooling. So that's the case right across the country. There are 2 months of the year for Kaitaia and Whangarei when their average temperature is above 20 degrees. That means that we're heating, we're trying to warm up, and our target should be 20 degrees. We're trying to warm up the inside of the house, or keep the inside warm, far more than we're trying to cool the inside. Now that means that on the next slide, you'll see this heat flow going through. Why is it doing that?
Heat rises, right?
No, not because heat rises. No, not because heat rises, because heat moves from warm to cool. So we're trying to get, or it's trying to get from the inside, from that heated space through to the outside. And that's why we put insulation in the way. We try and slow down that loss. We're trying to keep warmth in the building, but it's moving out anyway. So on our Ukrainian flag, we've got this idea of the warm part of the insulation, and as it goes through, I haven't drawn it as a gradient, but as it moves through, it's actually cooling down. So there's a cold temperature outside there, and there's a warm on the inside. Now, the blue is kind of useful because it might indicate moisture. Now, I'm doing this really carefully, or trying to simplify this just so that's actually, we can pick all this information up quickly. But if you imagine the pink arrow moving through is heat, or energy, and where energy flows, moisture goes. So energy is actually driving moisture out through that structure. As it goes out, and that air, or the place there on the blue is cooling down, the risks for moisture accumulation are increased. So as we're letting air and heat out through that, the air has a risk of leaving moisture behind on those cold elements, on those cold surfaces. So let's jump to the next slide, because we can expect that as we increase insulation, and I hear this occasionally, to avoid condensation in a roof space, we're just going to put more insulation in. Well, when you do that, you actually don't avoid the same risk. The risk is the same. We've just got more insulation, and you'll see the proportions of the Ukrainian flag stay the same. So there's a temperature gradient. It's still cold outside. It's still warm inside, and that gradient is just a little bit wider, if you like. So the issue hasn't changed. The cold temperatures towards the outside haven't changed. So let's jump to the next slide, because we're going to go back to the small scale again. Oh, sorry, that was that. Yep. So we've still got heat flow going out. It's still taking moisture with it. We've got nothing in the way in these drawings, and that's what I want to jump to on the next slide. It's this idea of a fairly typical build-up where we would put plywood to the outside of that rafter. So we're back to just a skinny skillion roof here. Plywood to the outside. The black line could be, it could be a torch-on, it could be another type of membrane like a TPO, but the reality is there that the plywood is stopping moisture going out, and the black line there, the membrane, is also stopping. In fact, it's preventing all of the moisture going out. So I want to point out here that the heat flow still goes out. It's still going out through that structure, through the insulation. It's cooling down towards the outside. So we've got cold plywood and we've got cold membrane there.
Yeah.
And the risks of moisture accumulation, we'll see that in the next slide, the moisture can't get out. And we're going to go to the next slide.
Not with a good membrane anyway.
There we go. That's sorry?
With a good membrane, the moisture can't get out. Yeah.
Yes, well, I'm going to argue that even if it wasn't there, the plywood, bear in mind,
Yes.
you have to have 15mm minimum plywood there for the safety of the people working on the top.
Yep.
So what's happening there? The plywood, the glue layers in the plywood are stopping moisture moving out. And that's why I've doubled up on the blue in there. It's not a risk of moisture accumulation there. It's a reality. Moisture will accumulate there. And you might argue, hey, what if I put plasterboard to the inside to stop moisture moving to? Plasterboard doesn't stop moisture movement. In fact, it's very vapor open. Yeah, okay, but what if I paint the inside of the plasterboard? Paint on plasterboard doesn't stop moisture movement. You'd have to go to a very, very special paint to be able to do that.
Yeah. So
the risks here will not just be risks, but they'll be reality of moisture condensing against that plywood. We've got a problem with that roof. My simple statement here would be don't. Hopefully, Scott, you'll be agreeing with me on this one.
Yeah, no, completely. And also another thing you've got there, John, is that timber framing, which obviously that's if that was timber or steel, that's going to conduct a lot of that energy. And obviously you've got a massive thermal bridge there, which is a risky point.
Yeah. So we've got heat transfer going faster through the timber and very fast through steel if that structure was steel. So we definitely have a risk. I haven't got any photos in this presentation, but unpeeling roofs on schools.
Not attractive, those photos.
No, it's not good. Okay, so let's jump to the options that we've got here. What do we do with this? So on the next slide, what we've got is this idea of, well, let's create a ventilation cavity above the insulation and before we get to the plywood. But I'm going to say to you a couple of things here. One of them is don't. So let me explain why I would be saying that. One of them is don't because the insulation is now reduced. So we've got less insulation here, and we've actually made the plywood colder by doing that. If you allow, so the heat movement is still going to go through, but if you allow that heat to drive moisture through towards the plywood, you've got this issue of a cold plywood layer where the moisture is going to stop. So if we jump to the next slide, I've got this idea of the moisture and the heat getting to that point, at which point what we try and design in is a ventilation pathway. Now that ventilation pathway is, I'm going to say it's possible, but it's not actually plausible or even sensible as a design. And let me tell you why.
Sensible, love that word.
One is we need moisture to be moved out of that structure, but we're relying on forces that we can't control. One of those forces is going to be the wind pressure. So we need to introduce wind, and by the way, wind is air, and air carries moisture. So while we're moving air through, and sure, it might be drier than the air which is in there, it will provide some drying, but we have to introduce it into that space. The second part of that is you need to start digging into your structure, and the complexity of actually designing that in is pretty challenging. So you can put your mushroom vents and your, all of that sort of stuff, eave vents have to be introduced and apex of the roof, all of those things. The other one is the pitch of the roof makes a big difference, and the pitch related to the color of the roof is. So can you understand all of this is starting to get really complex? So if you have a white roof, that's far riskier. If you have a black roof, that's less risky. Why? Because of the heat, the energy, which is going to be driving into that and creating some level of stack effect, some drying potential. So white roof, dangerous here. Black roof, less dangerous, but it's still complex. And the other part of it too is the pitch. You've got to be steep enough to provide some I guess, stack effect underneath there. But you can't go too steep, otherwise you end up starting to shade. On the other one is shading. So if you've got buildings around you that stop, I'm just going to say don't. To be fair, if this was designed in and you were an architect working with us, we would just say, no, please find somebody else. I hope that's really clear. It's very, very complex to make this work, even though I'll say it possibly can work. it's pretty risky. Let's jump to the next slide. We've spent plenty of time on that. What can we do? What are the options here? So here comes some words. They're real simple. They're open and closed. What I'm describing here is the idea of preventing moisture vapor moving into the structure, toward the top of the Ukrainian flag there, toward that cold area of the structure. So the heat is still flowing. In fact, if I put that pink arrow in the right spot, it kind of would be the same as our very first slides. It would be from the inside all the way through to the outside. The heat is still flowing out through the structure, but we're preventing the moisture moving out. The thin pink arrow rolling around there is that idea of ventilation. The moisture which you accumulate inside the building, well, hopefully we're not accumulating it, but we're certainly, by cooking and breathing and showering and cleaning, you're putting a lot of moisture into the home. You've got to get it back out. As we said before, windows can work, but the wind has to be blowing and you've got to be opening them and closing them and opening and closing them. So mechanical ventilation, definitely preferable. So let's go for the layers. The internal layer, I've called it closed.
Yeah.
It's actually not closed, not 100% closed. If we close that completely, we'd have to use or call it a plastic sheet. A plastic sheet is the quickest way to rot timber. So yeah, wrap timber up in plastic, see it rot. If we jump to the next slide, what I'm showing here is the idea that some of that moisture can move through, a small amount, but it can also get out on the top of that structure above that roof underlay, which is shown in purple. And I've called that open. So that means it's vapor open, means that moisture can migrate through it, but liquid water, rain, can't. So those are just properties of materials that allow us to put those in. Now I've drawn that arrow doing a big right hook and going up the roof. That's because there's going to be a structure, a cavity structure above that purple line, and then you're cladding on top. Yep. So we've got it closed from the inside, open to the outside. Do you remember that that's the opposite of what we had with the plywood on the top, which was closed at the outside and was a trap to that moisture which was migrating through the structure. So what can we do with plywood then? Let's jump to the next slide, because we've got this idea of the diaphragm, the bracing that you gain from plywood is super useful. It's a great platform to work on the top of that. So let's use that, and we can jump to the next slide. So let's use that, but let's put the insulation in the right place, and that's outside the structure. A couple of things going on here. The Ukrainian flag is still there. It's the same amount of insulation in this case. It might be, well, for fluffy insulation, which would be, a rock wool or pink bats or a polyester or any one of those products. It's going to be a lot thicker in proportion for the new R6.6 construction R value. So we're going to look at an option after this slide. But firstly, we've got this closed open approach here again. So in this case, it's not that dotted green line, it's the plywood that we're going to use. That plywood would be taped. It would have some kind of covering over it or around it so that we're not letting rain through this whole system, but we're not letting moisture. Now, I've probably just put some confusing language into that. So let me start again. We're trying to stop internal moisture flowing out through that structure. So we have a closed layer to the inside of the insulation. And in this case, we want to be open outside the insulation. Again, same principle as last time. We want the airflow to be outside the insulation line. Same things going on inside. Our heating, our ventilation, our air tightness is all inside the building, and now our insulation is outside. This is a warm roof. So if there was anything that you take away from this presentation, this is the warm roof. Why is it called a warm roof? Because the structure is warm. The structure is warm and it's above the risk of any accumulation of moisture through condensation. So the risk is up in the blue layer. And in this case, it's actually outside the structure. So we're eliminating, or we're reducing the risks. And finally, there's two more slides. One is just the starting point here, and then we're going to add one layer on top. So finally is this idea of a closed roof. Now I've drawn here the Enotherm PIR, so a polyiso. It's a foam product. It has a foil layer on the inside and the outside, so both sides of that product. So I just want to clarify one thing here. You'll notice that while I've drawn the insulation differently, the Ukrainian flag is still the same. The temperatures in there are still the same. But what we're doing is we're stopping moisture getting to the blue layer. We're stopping the risk of moisture accumulation because we're not letting moisture get there. So we jump to the next slide. We've got just a membrane on the top of that. Now, because you can actually go any color you like with that membrane. So we talked about a white roof being risky before. Well, actually, you can go white roof here because we're not looking for air movement through that insulation or around the structure to provide a drying potential. So we've got a closed. In fact, if you think this through, plywood's closed, the foil layer is closed, the next foil layer on top of the blue is closed, and then we've got a closed membrane on top. So what we're doing is we're allowing the insulation to perform. And all of those other rules still apply. Now we've got a pink arrow coming from underneath. We're stopping moisture moving. We're trying to slow down the heat flow. We've got a great product there, which I think, and you can help me with this, the insulation value of that PIR is about twice as good as fluffy insulation. Am I happily right there?
Yeah, yep. And it has excellent compressive strength as well. So you could easily float a deck on top of that roof. You can turn it into a functional space. You know, so it's a versatile product, definitely.
Yep. And you can go very, very low pitch, and I think even down to 1 degree on this as well, depending on the membrane. So depending on your water tightness layers on the outside.
That's right. Yep.
Yep. So that's the end of the bulk of mine, and then we're going to jump to a very flash slide. Oh, but sorry, just before we do, and it's going to come up in this one too. But you see the pink arrow from the top? That's rain, right? That's external conditions landing on that. But we don't want to introduce. We don't need airflow for drying. That's now just drainage. So let's jump to the next because it is this in action with a real product. And Scott, I'll let you kick in and describe this one.
Yeah, so John, you make a good point about the PIR insulation board. It has foil on both sides, but you can see in the render here, our system, the Neurotherm system, also has an independent self-adhering bituminous vapor control layer, or it's a vapor barrier, which is seated between the PIR and the supporting substrate. So that prevents any moisture passing up through into that insulation layer. This particular render shows our Nuralite 3PM, which is a bituminous torch-on membrane system. So that's code mark certified down to 1 degree fall. I mentioned about you can float a deck on top of this that would be used in conjunction with a deck pedestal, a Nurajack deck pedestal. So it's a really functional roof. You know, we have a membrane, a 3PG membrane, which has root inhibitor properties. So this could be applied to a green or a ballast roof buildup. So it's very, very versatile. But yeah, in terms of that nice continuous layer of thermal insulation, so it's what it states on the pack, essentially you will get plus more sun generally with the constructed R value. So it's definitely a better way to build. And you can see there in terms of the fixing, we've got a thermally broken flange, and that secures the PIR insulation board to the substrate there.
So the substrate itself, that actually doesn't matter what that is, right? If your insulation is outside the structure, that could be CLT, it could be steel frame, it could be timber frame, it could be concrete. So that's a real benefit of doing this warm roof approach, or at least insulation outside the structure, which is our definition of warm roof. That's an open season to work with whatever frame.
Absolutely, yeah. The render here, it shows on a metal tray, which is the most cost-effective substrate. You can have relatively great spans in terms of the supporting structure there. So it could be up to 3.5 meters internal spans for your supporting structure. End supports are less than that, but we're also seeing a lot of flat CLT construction, and the PIR board is available. It has a preformed taper. So what that means is your structure can be completely horizontal, and you can construct the falls using the preformed tapered PIR board with the membrane as your waterproofing layer. And like I say, we always have that independent vapor barrier between the PIR and the substrate. So that's best practice.
Yeah, nice. Well, and we were just talking about the multiple different substrates. You know, we're sort of open to anything. And obviously, in this example, all we're showing is a one membrane type that we have. Different multiple finishes, if you like, because we can finish that with a single ply TPO if that's your fancy. We're happy to guide you what we think's best. There's no such thing as a silver bullet, so we'll basically advise you on our experience which is best where. And we're not restricted to just membranes either. We can go back, we won't go back, but if we remember back to one of John's previous slides, we can actually use this warm roof concept whilst providing a rain shedding screen on top, whether it be a metal tray system, for example, where we do introduce an air cavity underneath that, but it's a little bit more complicated. But the point I'm trying to make is that we're not restricted, obviously, in substrates, as the guys discussed, and also not restricted in the top finishing either.
So you've got in your Nuratherm brands appraisal, I note that you've got all of the different substrates, or most of, or some of at least, named, but you've also got an existing construction option. So is this applicable for a re-roof as what we're looking at there? Like, can I take my roof with a corrugated iron and can I just overlay direct on that?
Yeah, you can.
Yeah.
In principle, yeah. If the existing metal tray is structurally sound and in good condition, then it can be used as an existing supporting substrate. We often see standing seam profile. We just add an H-grade polystyrene infill there to even out that surface. Then the vapor barrier goes down, PIR board gets mechanically fixed, and then waterproofing membrane on top. So it's definitely a lot better than having to deconstruct. So you're essentially rebirthing the roof. It's a far better way to build. And equally, the benefits of the warm roof approach that we've talked about. So there's no requirement to ventilate this roof. We're shifting the dew point outside of the building. So it's a very durable system. And the other thing is you can also overlay the system. We recommend after 30 years, you can just add an additional layer of the cap sheet there, and that will command another 20-year material performance warranty. After another 30 years, same process again. So potentially this build-up, I mean, that PIR, that's not going to settle over time. So in terms of the structural integrity, it's excellent. You can rebirth that waterproofing layer. So it can last up to 90 years plus.
Sounds pretty good. I don't really care that much about that, Scott. I'm going to be very dead by that time.
You just keep up with your
attitude.
You keep up with your cycling, John. Keep up with your cycling, mate. You never know. Yeah. All right. Look, what we'll do, if we just flick back to the previous slide, we're doing really well for time. We've had some really cool questions come through. We're going to do a bit of Q&A for about 7 minutes, and then we'll do a quick summary and leave you all alone. So I've got a couple of questions from the participants. A nice, easy one, I thought, to warm us up. So in the build-up, we're showing PIR board. What is the R value of a 100mm PIR board, for example?
So that's an R 4.5 with 100mm thickness. Yeah. So for the new requirements for the R 6.6 would suggest 150mm thereabouts as a starting number in terms of that thickness of PIR to meet the new schedule method requirement there.
Comparison with a fluffy insulation. Forgive me if that's the wrong word, but fluffy is
teddy bear stuffing we use.
Yeah. So that would be more like, or more than 300mm of insulation typically. So it's really is double the performance for a given thickness if you go to PIR.
What else have we got? Can we just touch on the difference between construction R value versus the R value on the label, on the bag?
Yeah, I'm happy to touch that. Hopefully it's what's stamped on the bag. So let's say let's say it's R6.6. Let's say there was a magical product that was super thick. It arrived on site and it said R6.6. That's a number which is from the testing of that product in a lab, but it's not the way the building is constructed. So if you think about those first drawings that I had, we had insulation between the rafters. So when you put insulation between any framing, so whether it's timber, steel, what other framework have we got? It doesn't really matter too much, but between the framing conducts heat as well, or better than the insulation. And so you need to factor that in. So what's a good example of that? If you've got 600 wide spacings on your studs, you've got approximately 500 or 550, if you like, of insulation between those studs. You have to account for the heat loss that's going out. So basically you're saying the timber stud is carrying some heat. Because it's carrying more heat than the insulation, you need to have some more insulation than that 6.6. So I've probably just used rafter and stud and roof and 6.6 in a bit of a combo there, which was a bit confusing. Even as I said it, it was confusing. Apologies. You've got losses through the insulation, and that's the term in there behind all that is thermal bridging that you need to account for.
Okay, cool. Another question here from the group. How would you go about learning the modeling method? How would you go about learning that?
That's a fantastic question. I don't have a direct answer on that. We use a combination of simulation software. We would draw in SketchUp a model and then import that into the Passive House planning package. So there are some plugins that operate between those two, and that gives you the ability to input the value of the windows and the frame and the installation values of that frame, the values of the walls, the thermal bridging. So every building has some level of thermal bridging. You just need to account for it, understand it, and then values of the structure and then orientation. And it's all for climate. So you're putting in very specific data around site and shading. So happy to answer some more on that, and I'll put you in touch. So Denise Martin is our principal analyst on the modeling side. She'd be happy to work through some of those options.
Okay, just a quick reminder to the audience that at the end of this webinar, there's a quick survey there if you'd like a follow-up. So if you've got something quite pertinent you'd like someone to follow up with, just hit the yes button and someone will be in touch. To be fair, I've got 227 questions coming in, so which is fantastic. Obviously a hot topic, pardon the pun.
Oh, nice. I like that.
You like that? We won't get through them all. But we've got some pretty hot ones here. Now, look, I'm going to try and, pardon me while I paraphrase this question. Very well written. I'm going to pull it to bits. Basically, the question is, no question the warm roof's the way to go. Hear what we say. However, where does this leave our current building stock?
I'm not sure.
One thing that came to mind is that we did touch on it, is the potential to retrofit a warm roof system. Should that be a viable option?
Yeah, I mean, that's definitely one option, looking at overlaying with a warm roof system. And it's really a case-by-case basis. And that's something that Nuralite can assist designers with, and obviously John and the team at Oculus there. Yeah, as I say, it's really case-by-case.
It's a very lowball question for me. Wonderful. I have just recently completed a Master of Architecture by project. So that was completed last year, and it was looking at existing housing, and it was looking at the walls and the windows of existing housing and how we can improve them. So that was a very nice way of promoting my research. That's not my point. Actually, I think the outcome is really useful for our existing housing stock. I looked at externally insulating, and I did use Rockwool, and I tested the installation details in our test booth here at the workshop, That information is available. That thesis is available on our website, on our resources page, and I think we're actually going to chuck up a link on that too. But yeah, so I'm not here for self-promotion. That information is there. It's a really good question. Our existing housing stock is of very poor condition. There's 830,000 homes with no insulation in the walls just to begin with. We're talking about roofs here and improving. Yeah, you can stick some fluffy insulation on the ceiling, that's a start, but actually the walls make an incredible difference to the performance and the comfort and the health of the occupants in those buildings. Great question.
Okay, cool. So out of the 200 questions here, I've actually condensed a few of them. They all go together. And I like that. Scrolling through, it's the price, and the price. To try and give you an example, the render that you're seeing on screen there, we are typically seeing that whole build up as you see it going on for around about $300 to $350 a square meter. That doesn't include daily parking or, I mean, we're just talking ballpark figures here. Now, when we're talking the membrane alone, so if you've got 2 layers on plywood, the typical market rate, I would imagine, would be between 150 to 160 a square meter. And you might think, wow, that's, the warm roof's a lot more expensive than the cold roof option. However, what you're not factoring in is actually the time and cost of the construction of the plywood structure that the membrane has to sit on. Now, I understand that plywood structure is around $450 to $500 a square meter just to supply and install, and the time that takes to. So you've actually got to look at the whole system holistically. And I think Scott mentioned earlier that the metal tray is quite economical. It's got great spanning capacity up to 3.5 meters. Whereas a plywood structure, depending on your membrane type, you're going to need structured every 600 or 400 millimeters each way. And the price of timber at the moment, well, price of everything, but price of timber puts it up there. So look at the whole project holistically, and I think you'll be surprised. So hopefully that answers the question on price. Another quick question here around about, where are we? Licensed installers versus available for trade sales. So just to clarify that, the system that you're seeing here is supplied as a system and is installed by a Nuralite approved applicator. However, the insulation board by itself is available to the market and to trade partners. So hopefully that clears that up. A quick question here on the heating cooling climate. Surely it's tropical enough here in Auckland, we don't need a heater, is it?
Yeah, and I know that's a really easy way to look at it, but look, it's not my information. Jump on the NIWA site, look at average monthly temperatures. The data doesn't lie there. It's simply this idea that we want to be continuously at 20 degrees and not above 25 all of the time in a building, not just when you get home, but all of the time. So the concept is simple. We need to heat internally to maintain that, and then rolling right back around to energy efficiency, we want to heat efficiently. So we want our insulation, we want the building envelope to perform sufficiently so that we can maintain that temperature efficiently or cost effectively.
Okay, cool. How are we going? Not too shabby. A couple more maybe. Where is it? How's the in the warm roof build up there? How's the insulation fixed in the warm roof build up, and how does this affect the performance?
So, like I mentioned, this render here illustrates a thermally broken flange, so it's mechanically fixed, but it's a wee bit tricky to see. You can see that the screw fixing, the metal fixing, is seated partway down the thickness of the insulation. So in terms of thermal bridging, it's mitigated by using this thermally broken flange. If that was a solid metal fixing, then obviously that's going to compromise or reduce the overall constructed R value of the system, and that would need to be taken into account and potentially increase the thickness of the PIR to offset that loss. But the Nuratherm system uses a thermally broken flange, so it does compensate.
Do you have glue on options for those layers as well? Just all glue, no mechanical, no screw fixing?
Yeah, it is available. It's not a standard pick and mix off the shelf, if you like. We like to get a little bit more involved with glue and adhesive fixing. We normally get third-party engineering involved to give us a PS1, for example, because we want to really make sure we get that nailed down. Again, another wonderful pun. John, we talked about this in the other week, actually. I think it's your favorite topic. And it was one of the slides we looked at, Scott, which we deleted, was the hybrid warm roof. Question here from Jeff. Can we have a 100mm PIR board on the top and 2.8 teddy bear stuffing in the structure and still call it a warm roof?
Well, isn't it called a hybrid warm roof? Look, yes, you can. Yes, you can. That's the starting point there. But like all of these, you need to know what that's going to do. So what we can do is some very localized modeling around that structure, that assembly, that build-up, to ensure that you're not going to accumulate moisture in there. And there's a rule which we would apply. I know my Ukrainian flag was a 50-50 sort of approach, and that 50-50 rule is not a bad one. That is that you'd have 50% of your insulation inside the, I'm going to stuff myself up here, 50% inside your air barrier and 50% outside. Now, typically that's safer if it's 1/3 of the value, not thickness, the value side, and 2/3 outside. But again, check it. We use WFI modeling to check that. So it's a high grade level modeling, looking at the way that heat and moisture migrate through materials and whether we are accumulating moisture in any of that part of the assembly or any part of the assembly. So yes, it's possible. The hybrid, yes, possible.
Check and the ratios there that they gave was 4.5 on the outside and 2.8 on the inside. Is sort of, along that 2/3 third, right?
Yeah, it sounds okay, but remember too that your critical path there is that you would be heating inside that building and ventilating to remove the moisture loading from those surfaces or from that, from the cooler. But and without going over complex, when you add more insulation inside, you're actually cooling down the layers behind that or close to the outside. So the more insulation you put on, look at it like, more insulation you put on, the colder the outside gets. Maybe that's a useful way to look at it.
Okay. All right, well, we're just about done for time. I just got one last one here. We might be able to touch on. It's when do these effects come in? When do these requirements for H1, when do they kick in?
That's a mixed bag. Maybe Scott, you do the insulation. I'll do the windows. So it is insulation, but windows, the changes are still happening for windows, and the dates haven't changed. So the window increase is still happening in November this year. And there's an interim, so there's a step change on the windows, so that all kicks in all together next year, which is the insulation date.
Yeah, so 1st of May, I believe, 2023 for residential, and it's November this year for commercial roof insulation requirements there.
Okay, cool. Probably best bet to keep an eye on the MD website there for the updates. We do know the dates have changed, but good to see a majority of the participants here actually sort of designing to the new standards now anyway, which we should do. Right, we're going to wrap up and do a quick summary. So hopefully this has been informative to you, not just another middle-aged white male webinar, and you've learned a couple of things from it. We hope that we've taught you what H1 is or what we mean when we say H1. We're talking about the energy requirements for a building. Hopefully we've illustrated what the changes are, what the new requirements are. Hopefully we've highlighted some of the unintended consequences of too much insulation in the wrong space. And hopefully we've illustrated what the best practice is. And I guess the big takeaway is we believe warm roofs are a superior method to achieve the new H1 insulation standard. I think we're just going to finish up on a poll. Is that what we're up to now? second poll. So yeah, get those fingers working. And this poll is basically just if you'd like to pick a topic for our next webinar. I'll give you a couple of minutes to populate that.
We could practice the last one there. Best practice for upgrading existing roofs. We could do that on my house and report back, couldn't we? That sounds like a really good charity. To
sorry, I think you're on mute, John. Okay, what do we got next? Yeah, so I'm going to populate that. We're going to show that poll. No, okay, it'll come out in the send out version along with I mean, give us a week or so to get those questions. There was quite a few there. Great to see a really high level of participation. Much appreciated. Always gives us something to think about. Some good challenging questions there. I know there was one there about plywood, which we look forward to coming back to the author on that. Plywood manufacturer versus membranes basically have got a different set of codes or rules, if you like, how they like it. But we'll go into depth of the answer on that. So more information on this topic, Scott, you've got some.
Yeah, so this designer's guide for H1 compliant roofs, which is produced by Outright Continuous Insulation. So as you mentioned, Shane, that's a division of Nuralite. This design guide really is a resource for all of the market, to be honest. And it covers a range of topics, things like high performance design, control layers, different roof solutions, different types of insulation supplied by Outright. So this is downloadable. It's downloadable from outright.co.nz. And
I think we'll also pop up the link to it in the chat function there.
Great.
Hopefully everyone can see that.
And it also complements, there is a wall. So similar principles, warm walls. Outright have produced a very helpful document, which is around high performing walls. So that is also downloadable off the Outright website.
Excellent. All right, we're going to wrap it up. Hey, thanks again for your participation. Again, a big thanks to the NZIA Merge Group. Great to have you on board. Good to see you all here. And just one last plug, Oculus have their own webinar today on heating and ventilation today at 3 o'clock. They've got something what I find interesting called the pen test. If you want to find out more, follow the link. I think there's a link coming up in the chat function there. Otherwise, you'll find it on Oculus's website. Look, thanks again for your participation. Thanks again for your donations to the charity, the Ukraine Emergency Fund, much appreciated. And we'll see you on the next one. Ka kite anō.